going to start with a talk by Yuting Chen, who's going to be talking about differential testing of JVM implementations. So please welcome Yuting.
Hello everyone. Next, I will present our recent work on testing of JVMs. I'm Yuting Chen from Shanghai Jiao University, China. Chen is a PhD student from East China Normal University. Chen and Zhendong are from UC Davis, and Jianjun is also from Shanghai Jiao University. In fact, testing JVMs is not an easy task. It requires painstaking effort in designing test class files along with their test oracles. We propose in the paper a coverage-directed fast testing approach. It helps to generate test class files for testing of JVMs and finding JVM defects. First, I will present the motivation of our work. JVM is a major Java technology. A JVM is responsible for loading, linking, and executing Java class files in the same way on any platform. All JVM implementations must consistently implement a single JVM specification. Meanwhile, a JVM is also very complicated. A JVM implementation, for example, OpenJDK's hotspot can have more than 250,000 lines of code. On the other hand, a complicated JVM must contain some defects inside. For testing a JVM, we prefer to find different types of class files and then run them on a JVM and find defects. Meanwhile, there still exists two main challenges. First, how is a JVM defect exposed? And second, how is a test class file obtained? For the first challenge, ideally we can get an actual result by executing the class of the JVM, and we can compare the actual result with the expected result. But where is the expected result from? The expected result can be inferred by checking the class against the JVM specification, right? Supposing that the specification is roundable, we should have a result that is absolutely correct. Unfortunately, the JVM specification is not roundable. In our study, we take another solution, that is to perform differential JVM testing. Differential testing is a promising approach that can reveal defects by comparing multiple JVM implementations. It operates by running test class files on several JVMs, and any detected behavior discrepancies may indicate the existence of JVM defects. In fact, our study clearly indicates that there exists some JVM discrepancies in JVM implementations. For example, this class file can reveal a behavior discrepancy between hotspot and JNI. This is a method. This method is in fact a class initialization method. It does not have the static flag, and this method, hotspot, treats it as an ordinary method, while JNI throws a class format error. The cause of this discrepancy is, in fact, related to an unclear definition in the specification, which we will explain later. For the second challenge, we also have some options. We can use real-world applications or use JIE classes as tests. They can reveal JVM discrepancies, but these discrepancies most only concern compatibility issues rather than actual JVM defects. An alternative is to blindly mutate the seeding class files and run the mutants on different JVM implementations. Let's revisit the previous example. The class can be created by renaming one abstract method as the class initial method. It can also be created by some other mutation activities. Even we found that domain-aware fast testing is effective. We have found more than 62 discrepancy triggering classifiers within 3 days, which will be presented in the evaluation part. So domain-aware fast testing allows a large number of test classifiers to be produced, including many invalid and unexpected ones. However, it's easy to create a problem of test redundancy. A large number of test classifiers can be created, while they may trigger only a very small number of JVM discrepancies. We propose a project called ClassFast. ClassFast is designed to, on the basis of 2 key observations. The first observation is that a class can encompass intricate syntactic and semantic constraints. Therefore, if we creatively rewrite classifiers, that the resulting classifiers can become corner cases that may certainly violate some constraints in the specification. If we rewrite the classifier, it may violate some constraints. The second observation is that many classifiers can be redundant, while the redundancy can be eliminated by partitioning equivalent classes and taking each test from each partition. However, this technique, black box testing technique, ECP, only works if we can decide that the 2 classifiers belong to the same partition. ClassFast advocates an idea of differential JVM testing. We use test classifiers to differentially test the JVMs, including different hotspot releases, IBM's J9 and GCC's GIJ. Furthermore, ClassFast mutates the seeding classifiers and creates as many mutants as possible, including many corner cases. And it uses the coverage uniqueness to select representative ones and leverages the MSMC, Markov-Chen-Manacaro sampling to guide mutator selection. Next explains the details of ClassFast. ClassFast includes 4 main components: defining mutators for mutating seeding classifiers, and deciding the representativeness of classifier mutants, selectively applying mutators using the prior knowledge and the differential testing of JVMs for finding JVM defects. For mutating classifiers, we designed 129 mutators, allowing the seeds to be mutated. Illegal constructs can happen to be introduced into test classifiers, which will further raise JVM discrepancies if they are handled by JVMs differently. And in the 129 mutators, 123 mutators are designed for mutating classifiers at the syntactic level. For example, given a classifier, we can change its some modifier from public to private, or from private to public. And the 6 mutators are designed for mutating classifiers through rewriting their Jimpo files, the suit intermediate representations. Given a classifier transforms into a Jimpo file, it then inserts, deletes, or replaces 1 or more lines of the Jimpo file, which may stochastically change the control flow of the class. To facilitate the further JVM testing, we supplement each mutant with a simple main method. The main method simply prints a message that the class can be normally invoked or normally loaded on the JVM. Thus, during testing, a test classifier can either be normally invoked or triggering some error or exceptions if the JVM fails in loading and invoking this mutant. It also leads to one limitation in our approach. Only the JVM's startup processes can be tested because the mutated program constructs or attributes may be less likely to be activated during execution. For the Java startup process, a JVM starts up by loading a class and invoking this main method. The startup process involves the steps of loading, linking, initializing, and invoking classes iteratively. At any step, the JVM may throw built-in errors and or exceptions when any constraints are violated. During testing, the test result of a class file can thus be simplified by checking whether the main method can be normally invoked or during which phase an error or exception is thrown. It helps us take a fine-grained analysis of the test results and make a comparison. The second component is to select representative mutants. The key idea for partitioning test class files is to decide whether two classes belong to the same partition. In our study, we select a reference JVM and later the two class files or other test class file mutants run on the reference JVM. If the reference JVM equally processes the two class files, they belong to the same partition. We choose hotspot for Java 9 as the reference JVM. We use coverage uniqueness as a discipline to accept or reject class files. That is, given two class files, the reference JVM must differently handle them if their coverage data are different. For example, for the two class files, the first test class file corresponds to a coverage of 7,000 lines of code and 2,300 branches when running on the reference JVM. And the second one corresponds to 7,020 statements. The two class files must be differently processed. When we have a new mutant, we can then collect its coverage and compare its coverage with the coverage data of the other tests in order to determine whether the new mutant is representative or not. We have defined 129 mutators for creating new class files. These mutators are not equally effective. In our study, class files rarely creates representative class files when using some mutators. And these observations underlies our design to selectively apply mutators for generating representative class files. The proposition behind this approach is that the more representative class files can be created by a mutant, and the more likely this mutant should be selected for further mutations. Class files adopts the Metropolis hasting algorithm for guiding mutator selection. And this algorithm is the MCMC, Markov-Chain-Monte-Carlo method for obtaining random samples from a probability distribution. Let the geometric distribution be the desired distribution that meets the proposition. We associate with each mutator a success rate, which computes how frequently the mutator has been observed to create representative class files. The mutators can then be sorted in descending order of their success rates. The first mutator has the highest success rate, while the last the lowest. This is the geometric distribution, the desired distribution that meets the proposition. We associate we can select the mutator, sample the mutators to meet the geometric distribution. The algorithm selects the mutator at random and accepts or rejects the mutators by a Metropolis choice. It's calculated as this. It's calculated by just using the desired distribution. We execute the class files on 5 state-of-the-art JVM releases and compare the execution results for revealing consistent behaviors. We denote a JVM execution as this shows, and a discrepancy can then be easily observed if given the same class file and the 5 JVMs behave differently. For example, one states that the class can run normally, while the other issues some errors. Since we only test the JVM's startup process, we do not use any test inputs here. However, a JVM discrepancy can still either be a JVM defect or a compatibility issue. Since each JVM depends on a specific environment, in order to check whether it's a JVM defect or a compatibility issue, we enforce JVMs against the same environment. However, it's usually not feasible in practice. That the JVM releases depend on the same environment. A JVM defect appears when the results are different. But what does it mean? Let's revisit the results that can be obtained during testing phase. We can take a fine-grained analysis of the test result with respect to a test class file. We can check whether the test can be successfully executed or at which phase some errors or exceptions can be thrown out. The 5 test outputs with respect to a class file can then be encoded into a sequence of 5 bits. And a discrepancy appears when the sequence is not of the same bits. For example, let the class be successfully executed on JVM 0, while the others some errors. We can say that JVM 0 misses catching some format errors. And we have implemented and conducted an extensive evaluation of class files against the existing class testing algorithms. We chose Hotspot for Java 9 as the reference JVM, and we used gcover and lcover to collect coverage statistics. Since the reference JVM implementation has 260,000 lines of code, and it takes more than 30 minutes to collect coverage statistics at each run. And thus, we just chose a package containing the shared files used in a JVM startup process for coverage analysis. The cost for coverage analysis is thus reduced to about 90 seconds per run. For seeds, we randomly chose 1,200 class files as the seeds. Within a limited time period, we can mutate the seeds sufficiently. Class files can utilize one of 3 uniqueness criteria. We let class files adopt this criteria respectively. We evaluate class files against 3 other algorithms that we designed for comparison. A random mutation algorithm, random files, and a gradient mutation algorithm. It accepts a mutant if it leads to some increased accumulated coverage. And a mutation algorithm that selects a class file only if they are unique. We call it a unique files. And all algorithms but random files are coverage directed to accept or reject mutants, requiring code coverage to be computed at each iteration. Each algorithm takes the initial sets of seeds, employ the same mutators, but follow its respective strategy to mutate the seeds. Our empirical evaluation is designed to answer 3 research questions. How many test class files can be generated within a limited time period? And how effective are the test class files? And can the test class files find any JVM problems or defects? In order to answer these 3 research questions, we have prepared several metrics for evaluation. During testing, we have several findings. Random fuzz generates 20 times as many classifiers as those generated by any other coverage-directed algorithm because it does not need to collect coverage data. In 3 days, random fuzz generated about 30,000 non-representative classifiers. Meanwhile, as a human engineer may spend minutes or hours on analyzing one classifier and the test outputs, random fuzz just shifts the cost of classifier generation to manual result analysis. Classifier generates the most number of representative classifiers and achieves the highest success rate among the coverage-directed algorithms. And the success rate ranges from 5% to 63%. In the guided algorithms, classifiers achieves the highest success rate. Classifiers can utilize the prior knowledge to select mutators. Although mutator selection does not very strictly follow the geometric distribution because the iterations are insufficient, it clearly agrees with the proposition. The higher the success rate of a mutator, the more frequently the mutator is selected. Comparatively, random fuzz selects the mutator without any guidance, even though some of them rarely creates representative classifiers. The frequencies of the mutators vary only because some mutators hardly create some classifiers. The third finding is that classifiers can enhance the ratio of discrepancy triggering classifiers from 1.7% to 11.9%. And it denotes that the tested JVMs are compatible for most of the classifiers, while still differ in processing some corner cases. Especially, we have classifiers can generate 900 representative classifiers within 3 days. It means that it can experience 900 different execution passes, while more than 100 passes will relate to JVM behavior discrepancies, a high percentage. During discrepancy analysis, we found that there are several root causes for JVM discrepancies. This program, as we have explained before, is caused by an unclear description in the JVM specification. For this program, it is mutated by setting the type of the only parameter of this method from map to string. And the GIJ throws a verification error for this class because it believes that it's unsafe to perform a typecasting between a string and a map, and the hostbot does not report any error for this. It denotes that the JVMs take their own classifier verification and type checking policies. JVMs are not compatible to access some errors, some classes. We add a strong exception to the main method. Hostbot reports an illegal access error for this class because it believes that some dot should not be used further. And the hostbot reports an illegal access error, while Jena and GIJ do not. We have more findings during discrepancy analysis. For example, GIJ behaves differently from hostbot and Jena because it conforms to Java 1.5, although it can handle the classes in Java 1.8 or 1.9, and many discrepancies are obvious JVM defects. And we collected 62 JVM discrepancies along with the simplified classifiers. And to the best of our knowledge, these discrepancies were previously unreported. Here is the conclusion part. Although domain-aware fuzzing has been employed in exposing defects in large-scale software systems, it has not yet been successfully employed in JVM testing. And in our work, we have proposed a coverage-directed approach to differential testing of JVMs. Our evaluation results have clearly shown that classifier is effective in yielding representative test classifier and finding some JVM problems or defects. And more information can be found at the website. That's it. Thank you.
We have time for some questions.
Hi, I'm Eric Cotton. Thanks for the interesting talk. So I was wondering, you explained that some of the mutations you do on the AST level and other ones on the level of GIMPL. And I was wondering why the difference and why not all of them could have been done on the AST or GIMPL level. Could you comment on that?
Yeah, ideally we can.
Okay.
The only case is that we muted the GMO5 because of some implementation reasons. And when I use suit, and it's not easy to just mutate the classifiers at the statement level.
Okay.
And we hope to do so. And so we mutated some GMO5s.
Okay. Thanks.
Hi, Mehmet Ahmed from UC Santa Barbara. So, according to your results, your class fuzz is the best amongst the coverage-restricted fuzzers. Is that correct?
When we designed several fast testing algorithms, we believe that class fuzz selects the mutators and with prior knowledge and accepts rejects the classifiers, and so that the classifiers can be more representative. So we believe that our algorithm is better.
Similar to that, if I read the graphs correctly, it was showing that rand fuzz even had a better chance of fuzzing. So even if I can fuzz just randomly without using any untrained approach, why would I need a trained fuzzer? Were there any discrepancies that the only class fuzz has discovered according to your results?
The actual case is that random fuzz can generate a very huge number of classifiers, and it's not easy for us to take a quick analysis of the test results and the reason for causing some JVM discrepancies, and therefore we decide to just pick up some representative ones, and that's the main reason for us for your question, whether we can find some spatial defects that the other algorithm that can not find some JVM defects that cannot find. And I can say that the capability of the fuzz testing is just depends on the mutators. As all the algorithms adopt the same mutators, so we cannot decide. Cannot say that.
Thank you. One more question?
Thanks for the talk and the interesting work. I was wondering about the way you classified the mutants into these different classes. You said that if they cover different statements or different branches, you say that they are in different classes.
Yeah.
I was wondering, did you ever get cases where mutants were different and did have slightly different coverage, but were essentially testing the same features of the JVM? I.e., did you find that sometimes that was too fine a grained level of equivalence classes?
Sorry, I did not catch your main
Sorry. Might you have two mutants that have almost the same coverage, but slightly different, such that actually you would like to regard them as being in the same class?
Yeah. It's like some coverage data analysis and ideally, if we have the same coverage data and we can take them as the same class because it may not easy for two classes that happen to be of the same coverage. And also we have some other coverage criteria to distinguish them and if they are really different. And
Okay, maybe I'll talk to you more about it later.
okay.
All right, let's thank the speaker.